Now the last part of this question says that we need to calculate the output, the output equivalent resistance looking at the collector without neglecting RO. So without neglecting RO. So we need to calculate the output resistance looking at the collector terminal, which is this point before the RO, before we reach RO. So since we are going to look at this point, again, you forget everything before you. You are looking starting from this point for the equivalent resistance, then you forget anything before you. So you are going to remove RO. Again, when you calculate R output, it's again the same thing. You have to calculate the Thevenin equivalent resistance looking from this point. Okay? When you calculate Thevenin equivalent resistance, what are the steps that we usually do? Usually, you deactivate any independent source. So if you have any independent source in front of you, you just deactivate it. So for example, when you look from the collector here, you have to deactivate this source because this source is independent. And this is a voltage source. When you deactivate it, it will become a short circuit. So basically the circuit will look like this. You will deactivate the V input, so the V input will become a short circuit. Then you have here Ri, then you have Rb, then this is R pi, and then you have Re here. So you have to be careful when you plot your circuit. Okay, then you have this dependent current source. You don't deactivate the dependent sources. You leave the dependent sources as they are. If the current here is I base, then this is beta I base. Okay, and you have a resistance RO parallel with it. And then we need to calculate the Thevenin equivalent resistance looking from here. If you have a dependent source in your circuit, you have to calculate the Thevenin equivalent resistance by connecting, assuming that you have a source Vx that gives you a current Ix, and then you say that R output will be the Thevenin equivalent resistance from the point there, which is Vx over Ix, and you try to get a relation between Vx and Ix that doesn't contain any variables. So you get a relation in terms of constants, which are the resistors, the value of beta, these constants, okay, Gm, but don't get a relation of R output in terms of a current, for example, or a volt, because current and voltage, these are variables. We don't know what are the values, what are the values of the currents and voltages, right? But we need to get this expression in terms of constants, similar to all the expressions that we got before. You have to get the expression in terms of resistors, in terms of beta, Gm, constants, not variables. Don't get an expression in terms of V, for example. You don't have to, or you cannot have V or I in the expression. So you have to cancel any V or I. So we have here to get a relation between Vx and Ix, okay, that contains constants only. So let's start. Let's try to analyze this. Of course, now once we deactivated this, Ri and Rb, they became parallel together, right? So we can simplify this circuit by making Ri and Rb parallel. So we can simplify the circuit like this. Ri parallel with Rb. If you would like, you can call it any other name, okay? And they are also series with R pi, so you can combine R pi in series with this, and you will get only one resistor. So you can combine these three resistors. Let's call them now R. Let's call them R. Let's say RS or RB dash RB. We had already RB before, right? So let's call them RG. RG will be R pi plus these two parallel together, which is Ri parallel with RB. Okay, and then we can just combine them in one resistor with a current I base. So we have here a resistor called RG. Okay, and then I'm not going to combine it with Re because this current is important to leave it separate. Huh? We cannot combine these two resistors because I need the current I base, because beta I base depends on the current in this resistor alone. So if you combine, this current will disappear, right? it will disappear from the circuit. So you cannot combine because you need this current here in this dependent source. So we leave it like this now. Let's see the relation between Vx and Ix. Vx, the voltage Vx equals the voltage across this resistor plus the voltage across this resistor. Okay? Of course, the current here, Ix will be distributed between these two branches and then it will combine again here for Ix. Let's first get a relation between Ix and Ib. Ix and Ib. Ix is going to be distributed, Ix here, which is the same as this Ix, is going to be distributed between this branch and this branch. What's the relation between Ix and Ib? You can say that Ib equals, it's a current divider rule. Ib equals Ix multiplied by the other resistor divided over the sum. Ib equals Ix multiplied by Re over Re plus Rg, right? But with a negative sign. Why? Because when Ix divides between these two branches, Ix divides, it will go this direction, right? So Ib now is going in the opposite direction, so you have to include a negative sign. So again, Ix here, it will be divided between these two branches and then it will combine again here to represent Ix. And then it will be divided again between these two branches. This is a current divider rule. The current in this branch equals Ix multiplied by the other resistor over the sum, according to the current divider rule. So I base, which is going in the opposite direction, will be negative Ix multiplied by Re over the sum. This is the relation between Ib and Ix. Fine. Now, we can represent Ix in terms of I base. So we can say that Ix equals negative I base multiplied by Re plus Rg over Re. This is Ix. Now let's look at the current at this resistor, because in order to calculate the voltage across this resistor, we need the current in this resistor. So let's call the current in this resistor, let's call it, for example, I1. What's the relation between I1, Ix, and beta I base? We see from Kirchhoff current law that I1 can be written as Ix minus beta I base. And already we have Ix in terms of, or I base in terms of Ix, so we can write I1 as Ix minus beta multiplied by I base, which is already negative Ix, so it will be plus beta Re over Re plus Rg. So again, I1 equals Ix minus beta I base. We replace I base from this expression, which is negative Ix, so it will be plus Ix multiplied by Re over Re plus Rg, and there is a beta here. Okay, so now we obtain I1 in this resistor in terms of Ix. So now we can say that the voltage Vx equals what? Equals the voltage drop here, which we can obtain in terms of Ix, okay, multiplied, which is the current multiplied by Ro, and plus the voltage here. The voltage across these two resistors parallel together is Ix multiplied by the parallel combination of these two resistors, right? We have a current here Ix, it will go to these two resistors parallel together, so we can say basically that Vx equals Ix multiplied by Rg parallel with Re. This is the voltage here, Ix total current multiplied by the total resistance, plus the voltage drop across Ro, which is I1 multiplied by Ro. And I1 also we can replace it with, in terms of Ix, as Ix multiplied by 1 plus beta Re over Re plus Rg, okay, and we took Ix a common factor, all of this multiplied by Ro. So we replaced I1 with this is I1, we took Ix common factor, okay, and we multiply by Ro. Now we have Vx in terms of Ix. We can divide over Ix in order to get R output. So R output will be Vx over Ix, which will be Rg parallel to Re plus 1 plus beta RE over RE plus RG, all of this multiplied by RO, and this is the expression for R out. Of course, after you do that, you can come here and substitute the values of RG, RE, beta, RO in order to get a number, and if you do that, you will find that you will get something close to 4.5 to 5 mega ohm. Okay, so again, numbers are not important. The most important thing is the expression. The expression is the most important thing for us. Okay, and then you substitute by numbers in the last step. So this is how you calculate R output. Of course, in this problem, it's kind of difficult, especially for the part of R output, because we have this RO. This RO makes it makes things difficult. But this is as a training for you of how to do circuit analysis. After you replace the transistor with the model, you do circuit analysis that you learned in the circuits course about calculating the Thevenin equivalent resistors and resistance in terms of other resistance in circuit, and in case of having a dependent source. So now we finish this problem. We'll see you in the next video with another problem.